Okay, let's take a look at how to solve some of these problems with electron configurations and orbital diagrams. The first one we're going to be asked to do is carbon. It says write the full, complete, longhand electron configuration. What we want to do first is find where is carbon at on the periodic table. So we see carbon's right over here on the periodic table. It's at energy level 2 in the P section. To do a full electron configuration, though, we need to work our way through all of the electrons that leads up to carbon. So we start out here by hydrogen, and as we go from hydrogen to helium, at that point we'd be at 1s2. There's no more room at level 1. The s orbital is completely full. We wrap back around now to level 2, and we start over at lithium. And as we move from lithium to beryllium, we're at energy level 2. We're in the orbital type s, and at beryllium we're at 2s2, the 2 representing 2 electrons. We move across now over to still energy level 2, but we're now in the p section. So it would look like this. We have 2p, and the superscript represents the total number of electrons in that p territory. So this would be 2p2. Now to do a shorthand representation, what we need to do is find what's the last noble gas that precedes the element that we're working on. For carbon, the last noble gas is helium that precedes carbon. So what we would do is we write helium inside a little bracket, and then we write all the parts of the electron configuration that comes after helium, which in this case would be 2s2, 2p2. And that would be our shorthand electron configuration. An orbital diagram represents the electrons for the atom in a different type of fashion than the electron configuration. An orbital diagram would look like this, where we have 1s, an orbital diagram would appear like this. We'd have a line representing the single 1s orbital, a line representing the single 2s orbital, and then because the p sublevel contains 3 orbitals, we have one line for each one. This would correspond to the m sub l values of +1, this would be 0, and -1. What we want to do for an orbital diagram is fill in all the electrons represented for the atom. Because it's 1s2, it would look like this. We have an electron, that's 2 electrons. The first electron drawn goes in arrowhead up. So we have for 2s, there's 2s1, that would be 2s2, and then 2p2, we have 2 electrons in the p orbitals. Now because we want to follow Hund's rule, which indicates we have 1 electron per orbital before we double up, it would look like this. We'd have 1 and 2, and then this would be our orbital diagram for carbon. The next part asks us to do what's called write the 4 quantum numbers for the element. The 4 quantum numbers are based on the last electron we've placed into the orbital diagram. So we're going to base the 4 quantum numbers on this electron. The 4 quantum numbers go in this order. We write n first, then we write L, then comes m sub L, and lastly is m sub S. For carbon, the n value comes from the energy level. So in this case, we're at energy level number 2 for that last electron placed into the orbital diagram. That makes the n value 2. The L value is what sublevel are we in? Now remember, L is equal to 0 if it's an s orbital. L is equal to 1 if we're in the p sublevel. Because we're in the p sublevel for this last electron, our L value is going to be a 1. The m sub L value represents what's called the spatial orientation of the different orbitals within a sublevel. The values that we can have range from positive L to negative L, represented by the +1, the 0, and the -1 under each orbital. In this case, the last electron got placed into the sublevel designated as, the orbital designated as 0, so the m sub L for this particular electron would be 0. The m sub s number then is the spin. For m sub s, if it's arrowhead up, it's a plus 1/2. If the electron is arrowhead down, it's a minus 1/2. Because this is an arrowhead up, this would be a positive 1/2 spin for this particular electron. And these four numbers would represent the four quantum numbers for carbon. Let's repeat this process now with the element magnesium. First, let's find the magnesium element on the periodic table. We have magnesium right here. It's at energy level 3 and it's in the S block of the periodic table. The longhand configuration is writing everything we pass through to get to magnesium. It would be 1s2, 2s2, 2p6, and then at magnesium we get to 3s2, and that would complete the longhand configuration for magnesium. Shorthand would be we go to the last full noble gas prior to our element. This is neon. We'd write neon, and then everything that comes after the neon, which is 3s2, and that would be our shorthand electron configuration for the element magnesium. The next part, the orbital diagram, for this element we're only going to use the shorthand designation, so all we need to focus on is the 3s outermost orbital. The orbital diagram would look like this. We'd have a line, and this would be our 3s orbital. And for the s, the only possible m sub l value is 0. This is 3s2, so we end up with one electron going in arrowhead up. The one paired with it goes arrowhead down, and this would be our orbital diagram for the element magnesium. The four quantum numbers are now n, in this order, n, then L, m sub L, and lastly m sub s are the four quantum numbers that identify this element. We focus on the last electron placed into this orbital diagram. Now that last electron, we're at energy level 3, so the n value is 3. We're in an s sublevel, and for an s sublevel, the L value is equal to 0. So the L is 0. The m sub L, once again, can range from positive L to negative L. For an s orbital, the only type of m sub L value possible is 0. So this becomes 0. M sub s, once again, if it's arrowhead up representing spin in one direction, it's positive 1/2. Arrowhead down, negative 1/2. The last electron placed in here was arrowhead down, so the m sub s number is a negative 1/2. And this would be our four quantum numbers for the magnesium element. Let's now take a look at a magnesium ion. By virtue of being a positive 2 ion, that indicates that this ion, compared to the atom from which it comes, the ion has 2 less electrons than the actual atom. Now magnesium, the atom, had this electron configuration: 1s2, 2s2, 2p6, 3s2. The outermost electrons get stripped off to make the ion. So the last electrons right here, the 3s2 electrons, those are removed from the magnesium atom to create a magnesium ion with a charge of positive 2. So these electrons get stripped off. This would now represent the longhand electron configuration for a magnesium plus 2 ion. The shorthand representation, we go back to the last full noble gas prior to this, which would be helium, and we write helium inside a bracket, and then all the things that come after helium, which would be 2s2, 2p6. This is our shorthand electron configuration. The orbital diagram, we would have 2s and a single line, 2p, 1, 2, 3 lines. For 2s, the only m sub l value is 0. For 2p, it's plus 1, 0, minus 1. The 2s has 2 electrons in it, so we have 1 up and 1 down. The 2p6, following Hund's rule, we go 1 electron in each orbital and then go back and double up to give us our 6 electrons in the 2p sublevel. This would be our orbital diagram for the magnesium 2+ ion. The quantum numbers now again go in the sequence of n gets written first, then L, m sub L, and then m sub s. The n is the energy level that we're at, once again focusing on the last electron that got placed into this orbital diagram. So we're going to focus on this electron right here. The energy level that we're at is energy level 2 because this is in the 2p sublevel, so our n value is 2. The L value tells us the sublevel. L is equal to 1 for the p sublevel, so our L value is 1. M sub L is the spatial orientation. In this case, that last electron got placed into the m sub L value that has a -1. -1. And then the m sub s is our spin. Arrowhead up, it's +1/2. Arrowhead down, -1/2. So we have -1/2. And then this would be our 4 quantum numbers that represent the magnesium 2+ ion. For the element arsenic, the longhand electron configuration, once again, we have to pass through all of the electrons that bring us to the location of arsenic. Now, arsenic is located here in the p block at energy level 4. Now, to get there, we had to pass through 1s2, that brings us to helium. 2s2 takes us to beryllium. At 2p6, that takes us to neon. As we get to 3s2, we're at sodium and magnesium. 3p6 brings us from aluminum to argon. We wrap back around. We're at 4s now. As we go potassium and calcium, that's 4s2. And there's a kink in the pattern. We go back to energy level 3 for the highest sublevel in 3, which is the D block. And we go to 3d10 as we work our way to zinc. And we're back at level 4. And we go 4p1, 4p2, and it brings us to 4p3 when we get to arsenic. The shorthand notation, once again, we go to the last full noble gas prior to our element, which is argon. We write argon, and then the configuration that comes after argon, which would be the 4s2, 3d10, and 4p3, to give us our shorthand notation. Now, the quantum numbers, again, goes in the sequence N, L, M sub L, M sub S. Because we're at energy level 4, our N value for the last electron, we're going to focus on the last electron, our N value is going to be 4. For the p orbitals, L is equal to 1, so our L value is 1. Our M sub L for the last electron, see the first one's +1, then 0, this is -1. And because it's an arrowhead pointing up, our M sub S value is +1/2. This would be the 4 quantum numbers that we have for